rewrite an expression containing powers, it means to rewrite, that's too fat. So that means to rewrite the expression without parentheses and without negative exponents. Essentially in math, negative exponents are illegal, with one exception, and that's scientific notation. In scientific notation, negative exponents mean something, so that's really the only time they're allowed. So in order to do that, we need to know properties of exponents. So we have product of powers, we'll have quotient of powers, we'll know what to do with negative exponents, if you take a power to a power, etc. So the first one will be products of powers. And first you need a common base. And if I have x squared, x is the base. Okay, and so common bases mean that they match. So in that case, if I have x to the a times x to the b, I'm going to add the exponents. So it'll be a plus b. So for example, if I have x to the 5th times x to the 9th, that's going to be x to the 14th. Or, you know, a to the 10th times a to the 27th will be a to the 37th. And the way this works is because x to the 5th is 5 x's. Right? And if I multiply that times x to the 9th, that's 9 x's, and I'm multiplying them all together, so I would count up all the x's and I would have 14. Well, you don't want to have to write all this out. That's annoying, especially when you get into large powers like this. So you just add them. But this is why we're adding them. Okay, quotient of powers is dividing powers. Okay, and x cannot equal 0 in this scenario. And that's because I'm doing division and I can't divide by 0. And when that happens, we subtract the exponents. So for example, if I have x to the 11th over x to the 6th, that's going to be x to the 5th because I'm going to do 11 minus 6. If I have x to the 4th over x to the 9th, this is going to be subtraction, so technically it's x to the negative 5th, but we don't do negative exponents, and we'll talk about that in just another second. Or you can look at it as when I do my subtraction, it's like a tug of war, and whoever was bigger wins. So the 9 won, so I still subtract, but it's going to stay in the same place as the larger number, and that's because with negative exponents, I throw them in the basement. Oh, yeah. Negative exponents aren't allowed. So whenever we have a negative exponent, we take the reciprocal. So if the negative exponent is here, we throw it in the denominator. If the negative exponent is already in the denominator, it comes to the top. So the negative exponents are not allowed. So for example, if I have x to the negative 2, that's going to be 1 over x squared. Or if I have 1 over x to the negative 10, that's just going to be x to the 10th. So wherever that negative exponent is, you put it on the opposite side of a fraction and make it positive. Power of a power. And a power of a power is when you take an exponent and you raise it to another exponent. Now this looks different than multiplication. I'm going to go back real quick. Multiplication will either look like this or it might look like this. But you're going to have separate bases with the multiplication. Power to a power, you have one base and then two exponents. And when this happens, you multiply them. So when you multiply two powers of common bases, you add the exponent, but when you raise a power to a power, you multiply the exponents. So for example, if I have x to the 4th and I raise that to the 9th, that's going to be x to the 36. And if one of them is negative and the other one is positive, it follows the same negative positive rule, so that would be x to the negative 20th. But I'm not allowed to have that negative exponent, so I have to throw it to the other side of a fraction. So put it in the denominator. Okay, a power of a product. A product is when I'm multiplying more than one thing together. So let's say xy to the a. This is kind of like distribution. I'm distributing the product, though, to everything inside, or the power. I distribute the power to everything inside the parentheses. So this is going to be x to the a, y to the a. Or if I already had exponents in there, oops, and I raise it to a power, I'm going to be distributing. So I will get x to the AC, y to the BC. So for example, if I had, let's just say 2x y squared, and I bring that to a power of 3, I have to distribute this 3 to every term in that product. So this will become 2 to the 3rd, x to the 3rd, y to the 6th, because it's 3 times 2, and 2 to the 3rd is 8. The power of a quotient is similar to a power of a power. I have a quotient, I take it to a power. I do the same sort of distribution to both the numerator and the denominator, and it's to everything in the numerator and denominator. So this would be x squared over y squared. If there's more than one, actually let me do that with a more general case. So if I had x, say y squared over z, and I take that to the 3rd or something, I'm going to distribute that 3 to everything inside. So it'll be x to the 3rd, y to the 6th, z to the 3rd. And the same holds true if there's numbers. Okay. I'm going to distribute this 4 to every term in the numerator and the denominator. So we'll get 2 to the 4th, x to the 8th, 3 to the 4th, y to the 12th. 2 to the 4th is 2 times 2 times 2 times 2, so that's 16. And 3 to the 4th is 3 times 3 times 3 times 3, so that's 81. Okay, 0 power is nice. Anything to the power of 0 equals 1. Always. So, doesn't matter how big my number is. If I raise it to the power of 0, it equals 1. Fractions raised to the power of 0 equals 1. Some big, long, variable expression raised to the power of 0, it equals 1. It doesn't matter. If you raise it to the power of 0, it's just 1. And the reason that works is because of the subtraction during a quotient. Because if I have x squared over x squared, well, if I do the subtraction, that's x to the 0. 2 minus 2 is 0. If I go the long way, that's x times x over x times x. And x divided by x is 1. And x divided by x is 1, and 1 times 1 is 1. So that's why it works. First, we need to define a monomial. So a monomial is a number, bless you, variable, or expression, or product. With no negative exponents. Okay. Also, no variables in denominators, and no variables under roots. Okay. So in order to simplify a monomial, we need to make sure. Oh wait, I lied. Darn it. We can have, this part's correct, no variables under roots. Sorry about that. Okay, when it's completely simplified, there are no powers of powers left. Each base occurs once. Okay, so you only see, for a monomial, you'll only see an x one time, or you'll only see a y one time. All fractions are simplified. And there are no negative exponents. So how do we do this? You're going to multiply all the like things together. So 2 and 3 are alike, so I'm going to multiply 2 times 3, and I'm going to get 6. The a's are all alike, so I'm going to multiply a to the negative 2 times a to the 3, and we add those. So that's, I'm just going to write it like this. Hopefully that's not too confusing, and then we'll simplify it out. And then I've got a B. There's nothing like it, so I'm just going to write it down. And I've got a C. There's nothing like that, so I'm just going to write it down. So I have 6A, because negative 2 plus 3 is 1. B squared C to the negative 2. But I can't have any negative exponents, so I have to throw that down in the denominator. And now it's simplified. Okay, I have a quotient. So I look at, again, I look at the like parts. So the Q's go together, and then the R's go together. Oh, I made it so you can't even read that exponent. Okay, so the Q's go together and the R's go together. Now we can do this one of two ways. We can either subtract the exponents straight away, and you get Q to the 2 minus 7, R to the 4 minus 3, which will give me Q to the negative 5, R, which will give me R over Q to the 5th. Or you can do like the tug of war version, where I do the 2 minus, or the 7 minus 2. I still subtract, but because the 7 was in the bottom, I just automatically keep the 5 in the bottom because the 7 was bigger, so it won. And then 4 minus 3 is just 1. So you kind of skip this middle bit if you do it that way. Okay, and finally we've got a power of a quotient, so I'm going to distribute that third to everything. And that's going to give me negative 2 to the third, A to the 12th, B to the 6th, and negative 2 to the third is negative 2 times negative 2 times negative 2, so that's negative 8. Which is a good time to take a little side note. If I have a negative number, so let's say negative x, and I raise it to an odd power, it's going to be negative. If I take a negative number and I raise it to an even power, it's going to be positive. We have a degree of a polynomial, and the degree of a polynomial is basically the highest exponent. Well, sorry, not the highest exponent, the highest degree. Oops. From a monomial. Okay, and the degree is the exponent sum in the monomial. Okay. Wait, don't go. Okay, so first of all, we need to determine if they're polynomials or not. And in order to be a polynomial, it can only be made up of monomials. So take, for instance, B. It has the square root of x in it. Well, the square root of x is not a monomial. So this is not a true polynomial. So there is no degree. Is. Okay. Here we're good. So this is a polynomial. So this is, okay, so that is a polynomial. And then here I have x to the negative third. Well, that's 1 over x to the third plus 2 over x squared plus 6. I have variables in the denominator, so these are not monomials. So this is not a polynomial. Okay? If it's not a polynomial, there's no degree. All right, so now we've determined this one is a polynomial, these two are not. So we can only find the degree of the first one. So what we do is we add up the exponents on the variables. So I have 4 plus 3, so this degree is 7. And here I have 5, so this degree is 5. So the highest exponent, or the highest degree is 7, so the degree of the polynomial is 7. So you just add the exponents, and whichever sum is the highest, that's the degree of the whole thing. Is this a monomial? No, so it's not a polynomial either. So no degree. Okay, here we look good. If there's no exponent on the variable, it's like little invisible ones. So this number's 6, this number's 7, this number's 2. So what is my degree? Okay. Why don't you guys try the next two? Okay, to simplify polynomial expressions, we're subtracting, we're adding. When we subtract, we have to distribute that negative, which changes all the signs. So this becomes 4x squared minus 5x plus 6. And then minus 2x squared plus 3x, and, oops, sorry, not plus 3x, minus 3x. And then plus 1. So I just essentially changed the signs. That's what the negative does. And then once the signs have changed, it's just a matter of combining like terms. So 4x minus 2x squared. 4x squared minus 2x squared is 2x squared. Negative 5x minus 3x is negative 8x. And 6 plus 1 is 7. Okay, if you're adding, you don't have to do anything. You just start combining like terms. So the x squareds go together, the x's go together, the numbers go together. And so I have 6x squared minus 4x squared is 2x squared. Negative 7x plus 9x is 2x. And 8 minus 5 is 3. Okay, so if we have distributive property, first we have to distribute, then we simplify. So 3x times 2x squared is going to be 6x to the third. So I'm adding my exponents. 3x minus 4x is negative 12x squared. And 3x times 6 is plus 18x. Then I check and see if I have any like terms, which I don't, so I'm done. Here I'm going to distribute this 2/3 x and then the negative 4. This negative, that minus sign, has to come with the 4 when you do your multiplication. Now to multiply everything by 2/3 x, when I multiply 2/3 times 3, this 3 and that 3 will cancel, and I'm going to be left with 2. If I multiply 2/3 times 6, 3 goes into 6 twice. And then I multiply. 2 times 2 is 4. And when I do 2/3 times 12, 3 goes into 12 4 times. And I do 2 times 4 to get the 8. Okay. If the denominators don't divide into the number you're multiplying by, you just multiply the numerator times the whole number and keep the same denominator. So for example, if I had 2/3 times 5, they don't divide, so that would be 10/3. So you just multiply like that. Okay. So this becomes, so 2/3 x times 3x squared is going to be 2x, because the 2 here, to the third. And then 2/3 x times 6x, well, 2/3 times 6 was 4. So minus 4x squared. And then 2/3 x times 12 is going to give me 8x. And then my -4 times -3 gives me positive 12. -4 times 7 is -28. And then the -4 times -10 is positive 40. Once I've got that part, I'm going to start looking for like terms. I have x squareds that are alike, and I have x's that are alike. So this will be 2x to the third plus 8x squared minus 20x plus 40. Added, we subtracted, we distributed, now we're going to multiply. There are two methods. One is kind of like a FOIL, and the other one is a table. So it's not exactly FOIL because we've got more than a 2 by 2, but it's like FOIL, and then we have method 2, which is a table. And I don't care which one you use, it's a matter of personal preference. I'm going to show you both. With the kind of like FOIL method, I'm going to multiply every term in the first by every term in the second. So you get that kind of a thing going on. And that's why some people don't like it, because it's kind of visually confusing. But so I'm going to do x squared times x, so I get x to the third. X squared times -4 gives me -4x squared. 4x times x gives me 4x squared. 4x times 4 gives me minus 16x. 16 times x gives me 16x, and 16 times -4 is -64. And then I add up my like terms. And my like terms in this case canceled each other out. The second method is a table. And when I make a table, it works kind of like a multiplication table. Actually, it works exactly like a multiplication table. And I just write my expressions across the top and the bottom, and x times x gives me x to the third. X times 4x gives me 4x squared. X times 16 gives me 16x. -4 times x squared. -4 times 4x. And then -4 times 16. The nice thing about the table is that your like terms line up on the diagonals. Also, it's kind of compacted and square, and if you like things to be visually very organized, this will work better for you. X to the third, -4x plus 4x, they go away, -16x plus 16x, they go away, and then -64. So you get the same answer no matter which method you use. The nice thing about the table is as you get into like multiplying larger and longer polynomials, drawing lines can get very messy and the table always stays relatively neat, but it's just a matter of preference. So we'll do another one. N squared times n, and n squared times 2, and then 4n times n, and 4n times 2, and then negative 6 times n and 2. So I get n to the third plus 2n squared plus 4n squared plus 8n minus 6n minus 12. Those were all the arrows. And then I combine like terms. Or again, if you prefer a more blocky version, and again, your like terms are lining up on the diagonals. Either way, you get the same answer. Okay, when you're dividing a polynomial by a monomial, you divide each one separately. So this is essentially the same thing as saying 6x to the fourth y to the third divided by 3xy plus 12x to the third y squared divided by 3xy minus 18x squared y divided by 3xy. Now, do you have to write out this step? No. You can, though, if it helps. But this is what you're doing. You're dividing each part of the numerator by the denominator. So what I get is 6 divided by 3 is 2. 4 minus 1 is 3. 3 minus 1 is 2. 12 divided by 3 is 4. 3 minus 1 is 2. 2 minus 1 is 1. And then 18 divided by 3 is 6. 2 minus 1 is 1. And then the y's are going to cancel each other out. Oops. So they go away. So like those will just straight cancel. Okay, if I have this negative exponent, that is going to throw this 3xy into the denominator. So this is, I don't want to do that in red. 18x squared y plus 27x to the third y squared z over 3xy. So this also indicates division because it's negative. And again, I'm going to divide each of these by the 3xy. So if I do 18 divided by 3, I get 6. 2 minus 1 is 1. 1 minus 1 goes away. 27 divided by 3 is 9. 3 minus 1 is 2. 2 minus 1 is 1. And that z didn't divide by anything. It just hangs out. Polynomial division. We're going to do like the straight long division, and then we'll do something called synthetic division. And you get to kind of decide which one you like best. Polynomial long division looks like regular long division. So I'm going to take that x minus 5, and I'm going to divide it into x squared plus 3x minus 40. Okay. I'm going to look at x. I kind of ignore the 5 portion at this point. And I say, how many times does x go into x squared? 1. one more x. Or what would I multiply x times to make it x squared? So x times x, oops, not there. Put that over the x. So x times x is x squared, correct? So I'm going to do x times x, so I'll get x squared, and then x times negative 5, give me negative 5x. And then I have to subtract that. Well, when I subtract this, x squared minus x squared is 0, and minus and negative becomes a positive, so I get 8x. And I bring down my 40. And then I ask myself, how many times does x go into 8x? Or what would I multiply x by to make it an 8x? Well, I'm going to multiply it by 8. And so 8 times x is 8x, and 8 times negative 5 is negative 40. And then when I subtract that, I'm done. I got 0. So x squared plus 3x minus 40 divided by x minus 5 equals x plus 8. Or, in other words, x minus 5 times x plus 8 will equal x squared plus 3x minus 40. So, do you see it's kind of another sort of factoring sort of a situation? But that's your actual answer. I'll do x minus 3 into x squared plus 7x minus 30. So again, I look at the x and the x squared. X times x is equal to x squared, so I'm going to multiply that, and I'll get x squared minus 3x. If I subtract it, x squared minus x squared is 0. 7 plus 3x is 10x. Bring down that minus 30. And then I want to know how many times, or what do I multiply to make an x into a 10x? I'm going to multiply by 10. And that's going to give me 10x minus 30, which if I subtract, gives me 0. So that gives me x plus 10. Because I want to show you what to do with the remainder. Let's say I divide negative a plus 3 into a squared plus 7a minus 11. Okay. To turn that negative a into a positive a squared, I'm going to multiply it by negative a. And I'm going to get a squared minus 3a. And then I'll subtract that, which will give me 10a, and I'll bring down that negative 11. And to turn negative a into a positive 10a, I'm going to multiply it by negative 10. So I'll get 10a minus 30. And I'm going to subtract that, and I'm going to get 19. Now I have nothing else to bring down, and there's nothing I can multiply by a that'll make it a 19. So this is my remainder. Wow, that looks awful. So how we write that, we'd write negative a minus 10 plus 19 over negative a plus 3. So, rewrite that. So your remainder goes in the numerator. And whatever you were dividing by goes in the denominator. And you just tack it on the end of whatever your answer was. Does that make sense? So that's how you deal with remainders. You just make them into a fraction at the end. So this is your dividend. And this is your divisor. Okay? And your dividend has to be in descending order. So 3, 2, 1, none. Okay? And if you have a 3 here and you don't have a 2, like if it just went 3 and then 1 and then none, you have to place a 0 to hold that spot, because you have to have all of the numbers in descending order accounted for. So you have to have all 3, 2, 1, and none. So if there's something missing, you put a 0 in. Okay? So I'm going to write these numbers: 2, negative 13, 26, and negative 24 from the dividend. Okay? And then I put a box over here. And since this is negative 4, I put a positive 4 right there. If it was positive 4, I'd put a negative 4 right there. It's the opposite sign. Okay? So that's the start. And then I draw a line right here, leaving space to write numbers in between. And I bring this number down. Oh, not subtract. Sorry, I wrote subtract, I meant add. Okay. I bring this number down and I multiply. On this row, I'm always multiplying. I'm going to do like a star like that for multiplication. And on this row, I'm adding. So 4 times 2 is 8. And then I do negative 13 plus 8, which is negative 5, right? And then I do 4 times negative 5, which is negative 20. And then I add those and I get 6. And then I do 4 times 6 and I get 24. And that gave me 0. Now this last number is the remainder. If there's nothing there, you have no remainder. If it's a 0, I mean. Okay, so now what do we do with that? Right, well, that's what I was repeating. These are our new coefficients. And we are 1 power down from where we started. So our highest power here was a 3. So now we're at a 2. So 2x squared minus 5x plus 6. That's our answer. So I take these numbers, and these are my new coefficients. So 2, negative 5, and then 6 is my constant. And like I said, we're 1 power down. So we started at 3. We're now at 2. Okay, so the nice thing about synthetic division is it doesn't take up as much space. I have 3, 2, 1, and none, so I'm good on that. So I start writing the numbers. This is a positive 3, so I'm going to put a negative 3 there. That's not a straight line. So I'm going to make a straight line. I'm going to bring down my 2. I'm multiplying across here, and I'm adding there. So negative 3 times 2 is negative 6. I add those together and I get negative 3. Negative 3 times negative 3 is positive 9. I add those together and I get 5. Negative 3 times 5 is negative 15, and I add those together and I get 0. So I have no remainder. So my answer here, we were at a power of 3, so now we're at a power of 2. Okay, 4, 3, oh, see how I'm missing a 2? Did you guys see that? So I need to insert a 0a squared, essentially, so that I have 4, 3, 2, 1, none. You have to have all of the spaces. So I go 4, 2, 0, negative 4, 12, so that I have all of the spaces taken. That's a positive 2, so I put a negative 2 in the box. Bring down that 4. Again, I'm going to multiply across the bottom. So negative 2 times 4 is negative 8. 2 plus negative 8 is negative 6. Negative 2 times negative 6 is positive 12. 0 plus 12 is 12. Negative 2 times 12 is negative 24. So that gives me negative 28. And negative 2 times negative 28 is positive 56. So I have a remainder of 68. Right? 4, 8, negative 6, 12, 12, negative 24. Yep, 68. Okay, so this is my remainder. So to write this up as my answer, I started at exponent of 4, so now I'm at an exponent of 3. It's positive, so I do plus 68 over a plus 2. So this is there.